would like to thank the organizers for the possibility to speak here. So the work I want to present today is motivated by the following question. So we consider a degree D real polynomial. And we are interested in studying its real roots. So let's ask the note ZP, the set, the real roots of P. And we are interested more precisely to study the number of real roots. So a natural question is the following one. How many real roots does P have if we pick it at random? So it means that we consider the space of real polynomials equipped with some probability measure. And we study the random variable which assigns to every polynomial the number of real roots. A first answer to this question was given by Kostland and by Schabensmail. So they proved that the average number of a random the average number of real roots of a random polynomial equals square root of D. So we will write the average number, or the expected number, which by definition is the integral over the space of real polynomial with the number of real roots, equals square root of D. So of course, now, this statement is not completely precise since I didn't say to you which probability measure we consider. So, the probability measure we consider is a Gaussian probability measure. Associated to the scalar product on the space of real polynomials, which makes this family an orthonormal basis. So what does it mean? We have a vector space together with some scalar product. And this produces for us a Lebesgue measure and then a Gaussian measure. What is a Gaussian measure? It's just the Lebesgue measure with some density such that we have finite volume, and then we normalize it such that the total volume equals 1. So, with respect to this probability measure, Kostland and Schabensmail computed the expected number. And now it is natural to ask what about the space of polynomials whose number of real roots deviates from the expected one. So from square root of d. And the theorem I want to present is the following one. So every time we have a sequence of positive real number, then the measure of the space of polynomials such that the number of real roots deviates from the right to from the left more than this fixed sequence times square root of d. This space goes to 0 faster than all polynomials in our fixed sequence. So for high degree, in sense of probability, there are really many polynomials whose number of real roots is near square root of d. And actually this theorem is a consequence of a direct consequence of the computation of the moments of a random variable, of this random variable. What is the k moments of a random variable? It's just the LK norm of this variable. So this is just the integral over the space of polynomials of the number of real zeros power k. And this theorem is the consequence of the computation of such numbers. So the k moment has an asymptotic expansion. The first term is just the expected number power k, and then there is, I computed the second term also, plus some error term. So of course there is a more geometric setting which I want to explain to you. In this more geometric setting, I will construct a probability measure which coincides with the Kostland-Schabbs-Meil measure in the case of polynomials. So here we consider some x a smooth projective curve over R, and we equip the x with some positive line bundle, also defined over R. So we have this line bundle, and once we have this line bundle, we can equip it, at least the complex point, with some Hermitian metric. So we have a Hermitian metric, and actually we consider a Hermitian metric such that, so this, let's say, compatible with a complex conjugation. And more important, with positive curvature. So I do not recall what is a positive curvature, so a curvature associated with a line bundle. But the important thing here is that omega is a volume form on the complex points of X, and also it induces a Riemannian metric on the real points of our curve. So once we have these objects, we also have, for every d, let's say positive d, we have an Hermitian metric on the powers LD of our positive line bundle. And then every time we have such a global section, we can consider the pointwise value of this Hermitian metric evaluated in these sections. So for every point X, we have this quantity. So it produce for us a number, and we can integrate this function over the complex points. And it defines for us a scalar product, which we denoted as L2 scalar product. And so again, the construction of probability measure is the same. Once we have some vector spaces with some scalar product, we have some Lebesgue measure and then some Gaussian measure. So here the constant is 1 over square root of pi times the dimension of the vector spaces. There's the exponential term times our Lebesgue measure. And important remark, in the case of X equal P1 of R, L O1 equipped with the Fubini study measure metric. We have the scalar product chosen by Kostland-Schabensmail. Let's say this vector space is isomorphic the real polynomial of degree d, and the L2 scalar product equals the Kostland-Schabensmail scalar product. Yes.
And so you get this measure on the projective space. How invariant is it? I mean,
sorry, which measure? The Gaussian measure?
Even the old one, or any of them?
Yes, what is the question, sorry?
Is
it invariant by the action of O2?
Or yeah.
Oh, yes.
It is.
It is.
How does O2 act?
We have the... sorry. We have the space of polynomials with what variable is isomorphic to the space of homogeneous polynomial of degree d in two variables, and it acts on the variables. And we have that for every polynomial, the norm with respect to this scalar product equals the norm is invariant by the action, I don't know what to say.
Sort of the only measure that's invariant with respect to O2, or are there many?
It's the only scalar product up to scalar multiplication.
Okay.
Welcome. So now we have a more general setting, and also the first question I asked, how many real roots does a real polynomial have? Here is how many real zeros does a random section have? So for every section here, we will denote it by ZS, the real zeros of the section. And the analog of Koslin-Schabbsmail theorem is a theorem by Gaillet-Level-Changer. So the situation is the same. We have some ample line bundle over a curve, both defined over R, and they study the zero of random section over I power of this positive line bundle. And they prove that the average number grows as square root of D, and once we normalized by this factor, this sequence converged to 1 over square root of pi times the length, let me write the volume, of the real points of the curve. Again, in the case we choose the Fubini statimetric such that the volume of P1 of C equals 1, the length of P1 of R equals square root of pi, and so this theorem covers asymptotically the theorem of Koslin-Schabbsmail. This sequence converges to 1. And in this setting, we have the same answer to the question, what about the space of real section whose number of real zeros deviates from this expected value? And we have the same kind of results. So every time we choose a positive sequence, then the measure of the space of real section such that the number of real zeros deviates from the expected one more than this sequence times the grow order square root of D. This measure goes to 0 faster than all polynomial in our sequence. And again, this theorem is a formal consequence of the computation of higher moments. So we have an asymptotic expansion also in this case. So I write the formula and then I will make a commentary. So the formula is absolutely similar. Again, in the case of P1, the length of the real locus equals square root of pi, so all its term equals 1, and we have the formula as before. So I do not pretend to explain, of course, all this formula today, even if some terms, each term reflects some geometry of the problem. So maybe I will explain why the first term is exactly the expected value, power k. But what I want to explain is the first step in the proof of this formula, which is quite geometric.
Excuse me? Was k your first term?
Here?
In the first, yeah.
K is a natural number.
You have k in the math.
No, this is the main point. We have this space, and for every k, the measure of this space goes to 0. I mean, it's not exponentially, it's morally exponentially, but it's not exponentially actually, but it goes to 0 faster than all polynomials. So how we compute such numbers? So we start with the case k equal to 1, so the expected number of real zeros of a random section. The quantity we want to compute, I repeat, is this integral. And the idea is that the function we want to integrate depends on some real points of our curve. So we want to transport this integral over the set of real points of our variety. And to do this, we define an incidence manifold. So it is the manifold composed by the pair section and real points, real point. Such that this real point is a zero of our section. So it turns out that this is a smooth manifold, which admits two natural projections. Over our space of real global sections and over the set of real points of our curve. And what are the fibers of these two projections? So here over section S, the fiber is composed by point X such that X is a 0 of S. So it is our set ZS I defined before. And what is the fiber over a point, a real point X? It is composed by sections such that X is a 0 of this section. So it is the kernel of the evaluation map at the point X. Actually, here, and actually as X is a real point, small x is a real point, and these are global real sections, it takes value on the real points of our line bundles. So now we have this integral over the space of global sections, which we can pull back on I. And actually this value is nothing different than the volume of our incidence manifold. So now we are on the incidence manifold, and we would like to write this integral as an integral over the base times an integral over the fiber. So we know now what is a fiber. And actually, of course, this equality is not true because this is not in general a product measure, but it is true if we put here some density, and the density turns out to be a rational function. In the numerator, we have the norm of the derivative of the section at S, and in the denominator, we have the normal Jacobian of the evaluation map. This is the co-area formula. So what is the normal Jacobian? We have some linear map, which is not, of course, a map between space of the same dimensions, but we can consider the kernel of this evaluation map, and then we restrict this map to the orthogonal of the kernel. And so the normal Jacobian is just the Jacobian of the evaluation map in the normal directions of the kernel. And in particular, if, and it is the case for large G, but if the evaluation map is surjective, then the normal Jacobian, so let's say, for example, the absolute value of the normal Jacobian is always positive. It does not vanish, which is nice, as we have this factor in the denominator. So now we have this function here, which is a function which depends on the end of our point x. And this kind of value, some pointwise norm of the section or of the derivative of section, it's computable thanks to some really nice theory of Bergman kernel. And it turns out that actually these values for large D only depends on D and not on the points, up to an error term which goes to 0. So now we can finish. We have this quantity equals the integral over the set of real points of this value. And now, thanks to the compacity of the set of real points, we can integrate this error term. And what we obtain is just the computation of the expected number. So now we can see why there is these volumes that appears in our formula. Any question? So let's try to use these techniques for the computation of higher moments. So the case k bigger than 1. So now what we want to compute is the following quantity. It's the integral over the space of real section of the number of real zeros of a section power k, which I like to see as the number of the cardinality of the Cartesian product zs power k. And now, following this approach, we can define an incidence manifold formed by sections and some k points such that this section vanishes at these points. But now we see that if 2 points coincide, these k equations degenerate to k minus 1. And if there are 3 points that degenerate, the situation is also degenerate. So what we have to do at least is to consider the set of real points power k minus the diagonal. So what I call diagonal is sometimes called the big diagonal, as at least 2 points coincide. So now with this definition we have a smooth manifold, and of course we have two projections to the space of real global section and to xr power k. So again, the fiber here is just zs power k minus eventually its diagonal. And more important, the fiber over point x is again the kernel of the evaluation map. This time the evaluation map sends each section to the values of the section at the points x1, xk. So in particular, this map is never surjective on the diagonal. So this turns out to be a real problem, as if we follow this approach as for the expected value, what we have is the following one. So again, this value, this integral, we can pull back this integral over our new incidence variety. And then we can pull back, or we can push forward over the set of real points power k minus the diagonal times the fiber. So the fiber again is the kernel of the evaluation map at these k points. So with again some density function which we have to compute. And as before, this density function is some rational function. At the numerator, we have the product of the norm of the derivative of the section, so no problem. But at the denominator, we have the normal Jacobian of the evaluation map at our point x1, xk. And so even if, so again, the normal Jacobian is some determinant, and on the diagonal this map is never surjective, the normal Jacobian will be 0, and so even if we estimate this function using some Bergland kernel techniques, we could not integrate the error term, as the error term could have some poles on the diagonal, so it could explode. And of course, this problem is due to the not compact compacity of x power k minus the diagonal. And the tool I use to solve this problem is a geometric construction due to Olver. It's called the multispace, which I want to introduce to you now. So we can forget for 5 minutes all this problem. This is a purely, let's say, topological construction. So we start with some smooth manifold, which is without boundary, but not necessarily connected, and not necessarily compact. And we consider the k-pointed curves in this manifold. So what is a k-pointed curve? Is a smooth curve in M, so one-dimensional real object. Together with k points on C, which are not necessarily distinct. So in this case, we denote by number of E the cardinality of xj such that xj equals the point xi, sorry. Then if we have two k-pointed curves, we say that these two curves have multi-contact if the following two things happen. So first of all, xi equals xi prime. So these curves intersect at these points. And second, the jet up to the order number of I minus 1 at the point xi of each curves coincides. So what does this mean? Let's start with some two k-pointed curve which have distinct points. So if we have, in this case, so of course the first here, the first condition is just this curve have to intersect at xi, and the second one is the jet up to order number of I, in this case all the number of I equal 1, minus 1. So the zero jet has to be the same. So it is equal to the first condition. So if and only if these curves intersect each other at point xi. But if we have 2 points, let's say x1, x2, which are the same, it means that these 2 curves have to be tangent at x1. And in general, this condition means that these curves have to intersect at point xi for every I up to order, with multiplicity, up to a number of I minus 1. So again, example. Then the 2 curves have to be tangent here. And what is the theorem by Olver? Is the multispace MK, which by definition is the set of all k-pointed curves under the relation to F multi-contact. Is a smooth manifold. So a remark, maybe in the case k equal to 2, this is just the blow up the diagonal of m times m. But as k is bigger than 3, bigger or equal, this is a smooth manifold but not compact, even if m is compact. So how we can use these multispaces in this case? So now for me, the manifold M will be the real locus of the total space of the line bound of LD. And the definition of the, let me say, a new incidence manifold, the right one, we build the set of section S and k points on the real locus such that the k-pointed curves S, the image of the real locus by S with the marked point S x1, S xk. This k-pointed curve has multi-contact with the curve xr, x1, xk. These curves we can see as zero section. Of this line bound. So what does it mean? We can see two examples. So if, for example, our point as before are outside diagonal, then what does it mean? We have the multi-curve and we'll just have the real locus, and these curves have to be multi-contact, so it just means that the section S has to vanish at the point xi. So at least we have the conditions we want before. But now if, for example, the point x1 tends to the points x2. So we have that the k-point in the curve, real locus of our curve, with the mark point x1, xk, has to be as multi-contact with the sections. So it just means that these two curves are tangent. And so what does it mean here? It just the sections vanishes at x1 and also its derivative vanishes to x1. And so now we see that our k equations do not degenerate on the diagonal. And so we can, after, with some work, use some Bergman kernel techniques to estimate our density functions. So I will stop here. Thank you.
Any question? You have the opportunity to use the microphone.
Consider the case where x is a curve. Can you consider the case of higher dimensional?
Yes, but there is some other analytical problem. So the geometrical construction holds for any dimension. This part actually is more or less the same, but there are some analytical problems with some Bergman kernel estimates. So the functions have some poles, and the problem seems to be a little bit of analytical nature. So at now I do not know an answer in bigger dimension. No.
Any other question? So we thank the speaker.
Thank you.